Hi, and welcome to this section of the Probability and Statistics Tutor. And in this section, we're going to continue what we started in the last section when we started talking about data sets. And we're going to continue in this section talking about the standard deviation and the variance of data sets. So let's just recall what we were talking about before. Okay, we have a collection of data, we call it a data set. Okay, and in the last section, we spent quite a bit of time talking about the mean, the median, the mode, and I told you that the mean value, the average value, is really one of the most commonly used parameters to describe a set of data. Knowing what that average value is very important because it gives you an idea of roughly what the data set is doing, the average sort of middle of the road value. Okay. It turns out that there's actually another parameter that's equally important to the mean that most of you probably haven't heard about unless in taking a class in statistics, which is what you're doing now, and that's called the standard deviation. It is absolutely just as important as the mean to understand what a set of data is doing, and you'll see that in a second. Okay. The first thing we'll start out to prove that to you is to tell you and to show you that if you have a class, like let's talk about grades because everybody understands grades. You have a class A and class B, or class number 1 and class number 2. Both classes have the same average grade. Let's say the average is 50. Pretty bad average, okay? But let's say both classes have an average of 50. It turns out that even though the average in both classes is 50, the actual grades themselves can be quite different from class to class, but yet they would still give you the same average of 50. And what we're going to do is we're going to explore how those grades look different from class to class, and it turns out the standard deviation is going to be very important to understand that. So let's go ahead and do that. Let's say class number 1 consists of the following grades: 20, 31, 50, 69, and 80. Okay? Now let's just calculate the mean value. Let's see what this is. Okay? The mean value is going to be the sum of the values divided by the number of samples we have. So it's going to be 20 plus 31 plus 50 plus 69 plus 80. All divided by 1, 2, 3, 4, 5. Okay, so we did this before. So the average value for class 1, the numerator is going to be equal to 250 divided by 5 equals 50. So the average grade in this class was 50, and it kind of makes sense. Some grades are pretty low, some grades are okay, and then there's one guy in the 50 in the middle. So the average value is 50. So remember that because it's going to be important. Okay, now let's go off and look at class number 2. The grades in class number 2 are 39, 44, 50, 56, and 61. Let's calculate the average of these grades. The average value is the sum of the values over the number of values that we have. So it's going to be 39 plus 44 plus 50 plus 56 plus 61, all divided by 1, 2, 3, 4, 5. 5 grades. So what happens if you add all of these up? If you put those in and calculate the answer, you'll get 250 on the top, divided by 5, which we already know from last time is equal to 50. So what have we done here, and why have I taken the time to show you this? What I'm trying to say here is these two classes, Class A and Class B, have exactly the same average, but these grades are totally different, okay? These grades, somebody had a pretty high grade, had an 80. Nobody has anything that high down here, okay? And yet there were some grades here that were really low, like 20 and 31, and yet no one has a grade anywhere close to that low. But yet, how can they have the same average? How can they have the same average? Because what you really have to visualize when you're looking at the average value is you have points, you have grades, okay? And what you're doing is, if these are your grades here, you're kind of looking for that middle of the road grade here that represents the collection, okay? So visualize this with me. What if my grades were very tightly constrained to be here? Let's say this is 50, and I had some grades lower than 50, and some grades higher than 50, or I guess lower and higher. You're looking at the camera that way. Lower than 50, higher than 50. But the grades themselves are pretty tightly packed. Well, I can have an average value of 50 because 50 roughly lies in the middle of these grades. Now, let's look at a different class. Let's say the grades vary a whole lot more, okay? Here's 50 in the middle here. Some grades are higher than 50, and some grades are lower than 50, but the spread is a lot bigger in the second class, let's say, or in the other class, okay? I can still have an average value of 50 that roughly represents the middle, even though my grades are so much farther apart in the other class. I'm just proving to you by example that you can have the same average value, but yet the spread, so to speak, for lack of a better word, how far apart the grades are around the mean can be higher or lower, but yet yield the same average value. So how do we represent that spread? Because I told you the average value is very important to understand what data set is doing. Obviously, it's very important to know what that average value is, but it's equally important, I think you would agree, to understand how far this data is spread around. Is the data very tightly centered around the mean? I mean, if the average is 50, do all of the kids have 51, 52, and 48, 49 for their grades? Are they very tightly constrained around the mean, or do they have some outliers down up here around 100 and down near 0, and the average is still in the same place? What parameter can we use to describe how spread this data actually is? That parameter is called the standard deviation. Okay, that's what it's called. The standard. Listen to the word standard deviation. What it really means is standard deviation around the mean. That's what it means. It's telling you the deviation from the mean on average. That's what it's saying. It's telling you the data is centered around the mean, but it deviates from the mean by some number, and we'll learn how to calculate it. And that number gives you a relative indicator of how spread apart that data is around the mean. That's exactly what it is. That's called the standard deviation. Okay? So what we're going to say here is in this example here, I'm going to guess here and just tell you and show you that the standard deviation, I'm going to call it SD for right now, for class 1 is greater than the standard deviation of class 2. And I haven't proven anything to you yet, but I'm just submitting that to you because these grades up here, they're centered around 50, but I have much lower grades and much higher grades. So this distribution is kind of spread out much more than this one. This one is more tightly centered around the number 50. I don't have anything up in the 80s, and I don't have anything down around the 20s. This distribution of grades is more tightly packed. So this has a smaller standard deviation than class 1, which has a larger deviation. So that's what that means, okay? So how do you calculate the standard deviation, all right? The standard deviation, some books just represent it with an S, okay, standard deviation. Most books represent it with this Greek letter right there, which is a Greek sigma, okay, the lowercase sigma. And the standard deviation is going to be defined like this. Let me write it down. It's kind of ugly looking, but let me explain what it's doing here. The square root of the sum of x minus x bar squared divided by n minus 1. Now, that is called the standard deviation. This represents, once you calculate this number, this represents roughly, on average, how spread apart this data is. If you get a very small standard deviation, it means the data is tightly compacted around the mean. All of the values lie close to the mean. If you get a very large standard deviation, it means the grades are spread about the mean by a larger margin and are kind of generally more spread out, just like class number 1 here, okay? Now, before we actually calculate anything with this, I want to ask you a few things, okay? First of all, this is called the standard deviation. You should already know what this x bar is. X bar is just the mean. So you need to know what the mean is in order to even calculate the standard deviation. N is the number of samples I have. Is the number of samples that I have. Now, what is this formula doing? Because again, I want you to understand what it's doing so we don't just blindly plug stuff in here. We want to understand how this represents and how that relates to the data set. Okay, so what's happening here is I'm taking the summation of, just look at the individual things I'm adding up. Summation means add up. What I'm doing is I'm adding up some stuff. I'm taking every data point that I have. So if these are my data points here in my grade set, okay, I'm taking every one of them and I'm subtracting from it what the mean is, okay? Now, some of the values in my data are going to be below the mean, and some of my values in my data are going to be above the mean. I mean, that's the definition of mean, right? Some of the values are lower and some of the values are higher than the mean, which is, roughly in the middle, okay? So when I do this subtraction, sometimes I'm going to get a negative number and sometimes I'm going to get a positive number. I mean, if the mean is 50 and I take, and I'm looking at the number 20, you know, if 20 is one of my data points, 20 minus 50 is going to give me negative 30. But on the other side, if I'm looking at the data point of 80, 80 minus 50, if 50 is my mean, 80 minus 50 is going to give me a positive number. So because sometimes I've got positive numbers and sometimes I've got negative numbers, I'm going to square the answer so that I always have a positive number. It's just a way to get around having those negative numbers there. So I'm subtracting each value from the mean, and whatever I get as an answer, I square it. Okay? And then what I'm going to do is I'm going to divide by n minus 1. Just forget about the minus 1 for a minute. I'm basically dividing by n. I'm dividing by the number of samples I have. So what I'm doing is I'm averaging this quantity. I'm adding up some stuff, and I'm squaring it. Yes, I'm doing all this ugly stuff to it, but basically I'm squaring it, and these numbers that I get, I'm basically dividing by the total number of samples I have. So I'm averaging that. Okay? And then finally I take the square root of the whole darn thing because I did all this squaring on the inside, because I don't want to have a square as an answer. So that is why I'm doing what I'm doing. This is why it actually represents the deviation, because look at what I'm doing. X minus the mean, for every value that I have, I'm finding out the difference between that value and the mean. So if my values are very close to the mean, if all of them are tightly surrounding the mean and there's not much variation, all of these little subtractions are going to be pretty small. The value minus the mean is going to be small. So I'm going to add them all, square them and add them all up and divide by the number of samples, and I'm going to take the square root, and I'm going to have a pretty small standard deviation. But if every value that I have actually is spread about the mean pretty far, you know, just like we talked about in class number 1 that has grades that go very far from the mean, then all of these little subtractions, when I take the value minus the mean, they're going to be bigger. And so I'm going to square them, and I'm going to average all of that, and I'm going to take the square root, and I'm going to have a larger standard deviation. So basically all I'm doing is I'm taking, for every data point, I'm taking the difference between him and the mean, and I average those, I square them because I want positive numbers. I average it, and then I take the square root to get rid of the squaring that I did, basically. And that's sort of the indirect measure. It's called the standard deviation, okay? So let's use the standard deviation and figure out, let's actually calculate the standard deviation of class 1 and the standard deviation of class 2, and let's see what they are, and let's see if it does what we think it does. So, going back to basics, for class 1, okay, the values were, I'm going to go write the values down again, 20, 31, 50, 69, and 80. And we also calculated that the mean was equal to 50. Okay, we already did that. And we want to find the standard deviation. So, what I'm going to say is the standard deviation, you can use either letter you want. Right now I'm going to just put both down to get you familiar with both, is going to be equal to the square root of the sum of x minus x bar squared over n minus 1. Okay, and then you take the square root. Now it's kind of an ugly calculation, honestly, but it's just you know, addition, subtraction, and division and squaring. You just have to keep it all straight. So here's how we're going to do this. What we're going to do is I'm going to put a giant square root sign here, okay? And on the inside, what I'm going to do on the top, I'm going to have, for each value, we're going to go off and we're going to do this. 20 minus 50 squared plus 31 minus 50 squared plus 50 minus 50 squared plus 69 minus 50 squared plus 80 minus 50 squared. You take every data value and you subtract it from the mean, and then you square it. Okay? And then you divide all this stuff by n minus 1. I have 1, 2, 3, 4, 5 values, so 5 minus 1. So you just have to do that math, and then that will give you the standard deviation. So on the top, on the inside of the square root, what I'm going to have, let me go ahead and draw another big radical here. This right here is going to be negative 30 squared plus negative 19 squared plus 0 squared plus 19 squared plus 30 squared, okay? And then underneath that, it's going to be divided by 4. Now notice what I said here. Some of these values are negative because some of these values occur lower than the mean, and so they're going to give you negative values. That's why we're squaring them all, to get positive values so we can average them. And then we're going to take the square root to kind of get rid of all that negative, all that squaring that we've been doing. So on the inside, what you're going to have here, when you do all this squaring and then adding all this stuff up, you're going to have the square root of 2252 divided by 4, which is the square root of 630.5. And so the answer is going to be, the standard deviation is going to be 25.1. 25.1. What does that mean? Okay, what it basically means is the mean value of this thing is 50, and the grades are spread about the mean on an average of 25 points. Okay, what it basically means, and I'm going to get into this a little bit more, it means on average that's roughly 68% of the values in the entire class here are going to fall within one standard deviation of the mean. So they're all going to fall between a 25-point spread, basically, about the mean. So what this really sort of means is, if your mean is 50, and here's grades going up and here's grades going down, okay, then what it really sort of means is, here is, let's see here how I'm going to write this. This is going to be 50 plus 25.1. This is 25.1 greater than the mean, and here is 50 minus 25.1. This is 25.1 points lower than the mean. This is one standard deviation around the mean. This means that 68%, and I haven't even told you where the 68% comes from. That has nothing to do with this, but I'm just telling you as a fact that when you have this, 68% of the values in your class are going to live within one standard deviation surrounding the mean, okay? So here I have a pretty big standard deviation. The point spread is, I mean, that's pretty hefty, 25 points. One standard deviation is 25 points on either side of the mean. Let's figure out what class number 2 does. Okay, let's see what class number 2 is, and let's calculate that. So, for class number 2, the values were 39, and there were different values, completely different values, 44, 50, 56, and 61. And again, the average value of this mean is 50, because we said that they were both equal. That was the whole point of the example. So the standard deviation is going to be equal to, I'm going to put the big square root symbol. And what you're going to have is 39 minus 50 squared plus 44 minus 50 squared plus 50 minus 50 squared plus 56 minus 50 squared plus 61 minus 50 squared. And this is all going to be divided by n minus 1. There's 1, 2, 3, 4, 5. So it's, again, 5 minus 1. So when I do this, if I subtract these values and then I square each one and then I add them all up, what I'm going to get on the inside there is 314 divided by 4 on the inside of the radical. And so what I'm going to have is a square root of 78.5. So I'm going to have the standard deviation, which is the same thing as the sigma thing, is equal to 8.9. Okay. So the standard deviation of class number 2 is 8.9 points, okay? Which means that even though the mean was in the same place, these class members are squished closer to the center. On average, they only deviate 8.9 points around the mean, which the mean is 50. So if I were to draw the equivalent diagram that I did for a minute ago, if you had the mean of 50, then the standard deviation would be, here would be 58.9, and here would be 8.9 points lower, and this would be one standard deviation. And I'll write it down for you in a little bit, but basically what it means is all of your values, on average, 68% of your values are going to lie within one standard deviation about the mean, within one standard deviation about the mean. So what we have learned, just to write it down, that the standard deviation of class 1 is 25.1, which is greater than the standard deviation of class 2, which is 8.9, and that kind of is reflected in the data as well. The data for class number 1 looks to be spread about the mean farther than class number 2. So it's essential, actually, when you're looking at data, not to just ask what the standard, what the mean is. I mean, for grades in class, we usually don't care so much, but it's actually very important. If if your mean is a certain number, without knowing the standard deviation, you'll have no knowledge of knowing, were all those grades really, really far apart? Did I have some really good students and some really bad ones? Or were we all pretty terrible with a mean around 50? It kind of lets you know how you placed among your peers, basically, is what it means. It lets you know, were you the guy that didn't do so well when everybody else did? Or did you all kind of suffer with bad grades or good grades together, is really what it means, okay? So that's sort of the thoughts on standard deviation. And there's one more thing I want to tell you with regard to standard deviation that's actually pretty important. You'll see it in your class. S is defined as the standard deviation. We talked about that. So S squared, or equivalent sigma squared, because we said this is a standard deviation symbol. If you square it, what you're going to get is going to be called the variance. Okay, I didn't present this first because variance is it's just not as useful of a term. Really, basically, they're the same thing. This is an indirect version of the standard deviation. The standard deviation tells you how many points you're deviating or so from the mean, roughly 68% of your samples, and the square of that is really an indirect measure of exactly the same thing. But in your book, you're going to see S squared and sigma squared. Don't be frightened by that. It just means you're taking the standard deviation and you're squaring it. It's giving you an indirect indication of exactly the same thing. Some formulas, especially later on when we get into the probability densities, will have sigma squared in there, and so it's just kind of convenient to have it defined there so that you know what they're talking about. Okay, a couple of points I want to mention to you about the standard deviation. Okay, I already mentioned this one time. 68% of samples fall within 1 sigma of the mean, which means 1 standard deviation of the mean. That means if this is my mean, okay, and this is my mean plus 1 standard deviation over here, and if this is my mean minus 1 standard deviation over here, if I have a collection of data and I calculate the standard deviation, 68% of the values are actually going to fall within this. It's basically telling you how squished your data is, or how much it's sort of not centered around the mean. It's just telling you how spread apart or how squished together it is. Okay, so about 68% of the samples are going to fall within 1 sigma of the mean, 1 standard deviation. I'm trying to give you some stuff to seize upon so you kind of know what this stuff really means, okay? About 95% of the samples are within 2 sigma, okay? So if this is 1 sigma, then this is 2 sigma. I should say x plus and x plus. This is the mean plus 1 sigma. This is the mean plus 2 sigma. That's all it is. And then here you have the same thing here. The mean minus 1 sigma and the mean minus 2 sigma. Okay? So if 68% fall within here, then if you expand that envelope to 2 sigma, then almost all of your samples fall within that. Okay? And then the final thing is roughly 99.7% of samples are within 3 sigma, 99.7. So again, if you were to go off to 3 sigma, you would add another sigma plus 3 sigma, and then the same thing you would have over here, x minus 3 sigma. And what it's basically saying is if this is the mean, if this contains 68% of your samples in your class and this contains 95%, if you go even farther, 99.7% are definitely going to be contained within 3 sigma. So they're kind of figures that you can use to kind of guess, okay, here's the standard deviation. It's giving you an indirect measure. Okay, within 1 standard deviation, roughly 68% of the samples are going to fall. Within 2, 95% of the people. If I go out to 10 sigma, darn near everybody, 99.9999999% of all the samples in the class basically are going to fall within there, and it's just sort of giving you a feeling for that. So let's go ahead and work another problem. What we want to find is what is the mean and the standard deviation of the service time of fast food restaurants when the following data is given. So the time that you sit at the checkout window before you actually get your food for different restaurant chains is 287 seconds, 128 seconds, 92 seconds, 267 seconds, 176 seconds, and 240 seconds. So those are some numbers that you pull, you pull up at the drive-thru, you stop your stopwatch, and this could be chain A, B, C, D, and this one obviously has the best time, and this one has the worst time, and so on. That's basically what that data is telling you. If you want to calculate the mean, then all you do is you add up your samples and divide by the number. Okay, so basically what you're going to do is 287 plus 128 plus 92 plus 267 plus 176 plus 240, and then you divide by 1, 2, 3, 4, 5, 6 samples. So on the top, when you do that, you're going to have 1190 divided by 6, which is 198.3 seconds. The mean value of all the restaurants, if you look at the aggregate of all of them, the mean value is 198.3 seconds. Now let's calculate the standard deviation, because we want to know, are these restaurants roughly behaving the same around the mean, or are they very far spread apart around the mean? It gives you a relative measure of that. So the standard deviation is the square root of the sample minus the mean squared over n minus 1. Okay? So the standard deviation is, I'm going to put a big square root here, okay? And what we're going to have is taking one sample at a time. 287 minus the mean of 198.3 squared plus 128 minus 198.3 squared plus 92 minus 198.3 squared plus 267 minus 198.3 squared, and unfortunately I ran out of room, so I'm going to continue this right here, plus 176 minus 198.3 squared plus 240 minus 198.3 squared. Okay, all of this stuff is in a bracket because I'm adding it all together, and I'm dividing all of this stuff, and it's all going to be under a giant square root. I'm dividing that stuff by 1, 2, 3, 4, 5, 6. 6 minus 1 is going to give me 5. Okay? 6 minus 1 is going to give me 5. So the standard deviation, when you do all that, when you take these differences and you square them, and then this difference and square them, and this difference and square it, and this difference and square it, and you add all that up on the inside, on the top, when you add all of that stuff up on the top, what you're going to get is 31065.34 divided by 5. 31,065.34 over 5. So that's going to be the square root of 621.3.1. So the sigma for this guy is going to be 78.8 seconds. So what this means is the mean was 198.3 seconds. That's the average value of all the restaurants, but the standard deviation is actually pretty big, 78 seconds, over a minute. So the restaurants are not all behaving, they're not all tightly compacted about the mean. On average, 68% of these restaurants are going to fall within 78.8 seconds, and the rest of them are going to be outside of that. So it's a pretty fat window there. I mean, if this is your mean, 78 seconds on plus or minus on either side, most of the restaurants are going to fall within there, and some are not. And so it's not very, if you had all of them behaving exactly the same or very, very, within a few seconds of each other, then this standard deviation would be much smaller, but it's actually fairly big. So in this section, we've covered a very important topic of standard deviation and variance. Variance is just when you take the standard deviation and square it. That's all it is. It's not really used all that much as far as a nice gut feeling to look at some data and figure out what it means. The standard deviation is much more friendly to use because the units of the standard deviation is seconds, just like the units of whatever it was you were studying to begin with. So you can really use a standard deviation to look at the mean and figure out how far about that mean on average your data is lying. It gives you a measure of how spread apart or how compacted that data is around the mean. So it's very important. It's useful just when you're looking at data sets, but it's also extremely useful when we get into talking about probability distributions, which we will be doing very, very soon.